Let's take a look at line integrals inside of a vector field. So we're going to be integrating along a curve, but that curve is going to live inside of a field. So let's say that we have some curve here, C, and we want to do a line integral in here, but you have some vector field. Let's say that our vector field, all the vectors are kind of pointing in this direction. Now, a good way to think about this is take a point on this curve and think about the vector field pushing the point, but it's got to stay on the curve, kind of like a roller coaster. It's fixed to the curve. Now, as the vector field pushes it, it's going to move it along this curve, but since the way that I have this drawn, the vector field's pointing kind of in this direction, of course, when it's, say, here, the vector field's going to be helping a lot more than when it's, say, here. Right? So to move this along, the vector field is only going to be helping as much as it points in the direction that it is moving. So if you think about a point, say, right about here, my vector field's not quite going in that direction. The point wants to move, oh, you don't see out there. The point wants to move tangent to the curve. That's where it wants to move, but the field's pushing it this way. So the question is, how much is the field pushing that point? All right. Well, the idea here is if this curve here, C is defined to be some R of t, right? We have it parameterized. And we want to know how much it's going in that direction. Where our field here, F, what we want to know how much it's going in this tangent direction. So in the tangent direction T here. So if we found F dot T, that would tell us how much the field's actually pushing it this way. Now notice we have kind of the field being a force and a distance that we're moving across the curve. So this is actually going to give us what work is. So the work to move a object along a curve in this field can be given by F dot T as we move along that entire curve. So we're going to do the field dotted with the tangent vector, because that's how much the field's actually pushing it in that direction. And we're going to add up that value all the way along the length of the curve, and we get ds. Well, we can get this into a slightly more usable form. By the way, that's around C. So if we integrate around C of F dot, well, we know our tangent vector from before is R prime of t over the magnitude of R prime of t. And from the past, we also know that ds is the magnitude of R prime of t dt, which gives us, this is the integral around, man, come on, C of F dot R prime of t dt. You can actually clean this up a little bit nicer too, because we know that R prime of t is really just dr dt dt, it's a dot right there. So we can actually summarize this as the integral across the curve of F dot dr. Now this is one of our most basic formulas for work. We do the force dotted with the derivative of the direction that it's going. We add that up all the way along the curve, and that will tell us the work done as we move. All right, so let's try a very, very easy example of this. Let's just say if I said find the integral around C of F dot dr, and let's say that C, let's do a really easy one. Let's go from 1 to 2, say here. Let's say we're just moving along a straight line that way. That's our curve C. Now, since we only have one piece, we're only going to need one parameterization. So if we're moving that way, let's say the parameterization of this curve would be really easy to do. Let's let x be the parameter, and I know x is going from 0 to 1, so that's just t. And on this curve, that's the line y is equal to 2x. So if x is t, y is equal to 2t. So very easy parameterization for this. So let's see if we can find the work done by moving something from the origin to that point 1, 2. So we would set this up. We need to figure out what f is. So on C, Oh, I didn't give us a field. Let's say that our field here is y squared x. Just made that up. So that's a field has to be given so you know what field you're working in. Okay, so let's say this is our field. So when we're on this curve, what value does this field have? Well, as long as we're on that curve, all x's are t's and all y's are t squares. So when we're on C, our field is actually y squared, y is 2t, so that's going to be 2t squared, and on our curve, x is t. So we get that this is 4t squared t. Now, what is what is dr? Well, dr is the differential of this curve here. So the derivative of this is just going to be the derivative of the x is 1, the derivative, the x component is 1, the derivative of the y component is 2 dt. Okay, so this is just the derivative of this in differential form. Okay, so let's put the two pieces together. We're going to integrate across our curve C of f 4t squared t dotted with 1, 2 dt. We're integrating with respect to t, and on this curve, t goes from 0 to 1. So the integral from 0 to 1, that's going to be 4t squared plus 2t dt. 4/3 t cubed plus t squared evaluated from 0 to 1. Top endpoint's going to give me 4/3 plus 1, which is 7/3 minus 0. Okay, so we got 7/3. Now 7/3 what? Well, it's work. So you know it's a force and a distance, so you'd have to see what units this problem was actually in. All right, so fairly simple. So notice when we have to find the work, you have to parameterize the curve. You have to see what the field is on that curve. You have to figure out the differential of the curve, put it together in the formula, and integrate. All right, we're going to do the same problem again, but I'm going to change it just a little bit. What instead if we went from the origin to the point 1, 2, what if the only difference is we went the other direction? What would that change? Well, let's see. Okay, well, our parameterization is going to change. So we would say r of t is equal to. Again, if we use x as our parameter, since we're going from 1 to 0, we kind of want to think about this as going from 0 to 1. We've kind of seen how this works. We can write that as 1 minus t. Now on this curve, that's our x value. On the curve, y is twice that, so that's going to be 2, 1 minus t. So there's the parameterization for the curve when we start at the point 1, 2 and end up back at the origin. So let's see what happens when we put this together. So when we're on our curve C here, our field is going to be equal to the y component squared. So our field is going to be equal to 2, 1 minus x squared, and just the x component, which is 1 minus t. 1 minus t. All right, so our field on this curve is going to be 4, 1 minus, that's a t, I'm going to go next there. 1 minus t squared, 1 minus t. dr, when we're on this curve, if this is r, it's the derivative of this in differential form. That's going to be -1 and -2 dt. So we're going to do our integral of f dot dr around the curve C. This is the integral. Well, t runs from 0 to 1, just like before. That's our parameter bounds. F dot dr, well, that's going to be -4, 1 minus t squared, -2 times 1 minus t dt. All right, a little uglier than the last one. I think we can clean this up a little bit. Let's do a U-substitution. If we let u be equal to 1 minus t, because that's what I have everywhere I have a t, du is equal to -dt. So since both of these terms have a negative, I can actually write it like this. Let's see, 0 to 1. This will be 1 minus t squared plus 1 minus t and negative dt. I just took the negative out of both of these pieces and put it over here. Now we can do our substitution. This will be 4u squared plus 2u, and negative dt is du. Now I don't want to back substitute, so let's go ahead and put our bounds in here. If t is equal to 0, that would be this bound right here. If t is equal to 0, u is equal to 1. And if t is equal to 1, u is equal to 0. So instead of my bounds going from 0 to 1, my bounds go from 1 to 0. All right, so that's going to be 4/3 u cubed plus u squared evaluated from 1 to 0. Top endpoint minus the bottom endpoint. Notice you get 0 when you put that in there, minus 4/3 plus 1, so we get negative 7/3. All right, now it's not up here anymore because we have limited space, but notice that answers the exact same the same number, but the opposite sign is the answer we got before. So when we went in one direction, we got a certain value. When we went in the opposite direction, well, we got the opposite value. That should make sense, right? If you do work in one direction, when you go the opposite direction, the field's going to do the opposite amount of work to you. So we can write this as a result, a very important result that says this. If we're doing the integral of c of f dot dr, we're finding the work along some curve, well, that's going to be equal to the negative value of f dot dr if we do the opposite of the curve. Now, this is kind of a weird notation because this is talking about a curve. All this means is whatever direction we went on this curve, we go the opposite direction for that. So negative c just means the opposite direction. So the nice thing about work done by a field, whenever you do one way, you get back going the other way. All right. There's another way that we can look at work here, this integral f dot dr. There's a differential form that is also fairly useful. And let's see if we can come up with that real quick. I'll do it right here. There's what's called a differential form of f dot dr. Now for this, remember generically f we gave as mn, or in 3 dimensions was mnp. And from a second ago, we saw that dr was really dr, dt, dt. Let's see. So and we know that dr, dt, that's just a derivative with respect to t of our vector r is x prime of t, y prime of t. All right, so let's put all this together, and we're gonna have to shift around a few indices, and you'll see what I mean by here. Let me write this a little bit different because we're gonna need this in a second anyway. Let's go ahead and write this as x prime of t. Let's write that as dx dt and dy dt. You'll see why in just a second. All right, so if we put this together and I rewrite this as f is mn dotted with dr. When we know dr is dr dt, dr dt dt, so it's going to be dr dt, which is this, dx dt, dy dt, dt, right? Dr dt dt. All right, when we do our dot product here, this again around our curve C, we get, I'll put it in parentheses, m dx dt plus n dy dt dt, it's just a constant multiple on the outside. And notice, if we bring the dt inside here, we get the integral of m dx plus n dy. All right, so if you see an integral around the curve like this, and you have this form on the inside, some function in the x direction plus some function in the y direction, this also represents work, right? Because all I did was rearrange this. Now sometimes this form can be very, very helpful to use. Sometimes if you already have things parameterized, it's rather nice. Let's take a look at what we just did. Let's say if I gave you this integral c of y squared dx plus x dy. Now notice the m and the n here really came from our field. So notice this is the exact same field that we had for our last couple examples. So in this case, we really don't need it, but you can see that the field here is y squared x. All right, let's say that our curve was defined exactly the same way that it was a second ago. 1, 2, there, and this is y is equal to 2x. Now, the nice thing about the differential form, especially when you already have your curve defined as functions of x's or functions of y's, is we can just use this form directly. So let's plug in what we know. Now, for here, I'm going to leave the bounds on, just put c there for a second. Here, since I know y is a function of x, I need to either get all of this in terms of x's or all of this in terms of y's. Since y is the dependent variable here, I'm going to get this in terms of x's. So on this curve, what does y equal? Well, y is equal to 2x. So that's going to be 2x squared dx plus x. Now what does dy equal? Well, from here, since y is equal to 2x, dy is equal to 2 dx. Now, since I have it all in terms of x, for this region, what does x run from? Well, let's go ahead and say it just goes from 0 to 1 in this case. All right, if we integrate, let's see, that's going to give me 4x squared plus 2x dx, or 4/3 x cubed plus x squared from 0 to 1, which of course is just 4/3 plus 1, or 7/3. So notice in differential form, of course, we get the exact same answer. The nice thing about differential form, if you already have y's as functions of x's, you can just change everything in terms of x. Basically what you're doing is you're parameterizing this in x's instead of t's, but it works out exactly the same way.